the video for Lesson 2, Tests About a Population Proportion. So we're finally going to get into actually doing these tests rather than just talking about what they mean. That's what Lesson 1 was about. I attempted to actually fill out some stuff beforehand so it wouldn't be like a 7-hour long video. Sorry about how long Lesson 1 was, so I'm just going to try and take some steps to make things go a little quicker, but that does mean that if you are actually trying to write this down, probably going to need to stop and pause from time to time because, again, you're not going to be able to keep up with me when I already have all of that written out. So just a heads up. So last section there was a basketball player who said that he made 80% of his free throws, and we thought he was exaggerating, so we took a sample of the 50 of his free throws and he made 32 of them. So there is some evidence that it's lower than what he's claiming because the sample proportion was 0.64. So it's lower than what he claimed, but we're trying to see if it's convincing evidence. So we need to check the p-value. There are first a set of hypotheses that we wrote where he's claiming that it is 80. The alternative is what we're seeing if we have evidence for. Is it actually less than 80? And the variable always gets defined, which is the tedious step, but it's the true proportion. It's always about a population parameter, never about your sample statistic. When we do this, we have to check our conditions. They're really similar to when we checked at interval. So the first condition is the random condition. If you don't have something that is random, you can't, it would be essentially like an observational study and you can't make extrapolations to the population, which is the whole point of doing this. So the data come from a random sample from the population of interest. The 10% condition is so that you can use formulas if you don't have the replacement issue, that is. So sampling without replacement, if that is the case, so if you're just taking a simple random sample, you don't have independence, this is how we get around that still. So it's where your sample size is less than 10% your population size. So it was like that before, still is. We talked before, when we were still in school actually, about how if there's an experiment, you don't really have to do this because there's no sampling from a larger population. So experiments are a bit different, but still. And then the large counts, slightly different. You're going to check in, and we don't know what P actually is. That's why we're testing it. But remember, hypotheses tests are built on the contingency that, whoa, that's a weird shape, that null hypothesis is true. So we're just going to use whatever p-value is in the null hypothesis. So it's denoted as n p naught. So as long as n times p sub 0 and n times the complement of the parameter in the null hypothesis, as long as they're both at least 10, then you can proceed. So from that basketball player, I already wrote up that the random condition is met because they can be viewed as a random sample from the population of all possible shots. However, this one's not sampling without replacement from the population, so there's not like a set of already made shots that we pulled some out of. He could just keep shooting. So we don't need to check the 10% condition is what I'm saying. The large counts condition, so assuming the null hypothesis is true, which all significance tests do, we're going to use p as 0.80. So then n times p naught is 50 times 0.8, so 40. And n times the complement of p naught would be 50 times 0.2, so we get 10. Since they are both at least 10, we can proceed and actually do this hypothesis test. So just a practice of going through those conditions for different problems. According to the U.S. Census Bureau, the proportion of students in high school who have a part-time job is 25%. So that is the statement that they're just starting out with. We think that is the true statement. However, an administrator at a large high school suspects that the proportion of students who have a part-time job is less than this national figure. So we're going to seek evidence to see if that population parameter is actually less than the null hypothesis is stating. We're going to carry this out at the 5% significance level, and P is being used as the true proportion, the population proportion of all high school students who have a part-time job. So she selects a random sample of 200 students from the school, finds that 39 of them have a part-time job. We're going to check the conditions for this hypothesis test. So the random condition, I can see here that she selects a random sample of 200 students. So that's what I'm just going to note. The 10% condition, I need to check the sample size. Again, she chose 200 students. So that's my sample size. I need to confirm that it's less than 10% of the population size. So if I'm talking about 200 students from the school, that's my sample. So my population would be the whole school, which they don't tell me the actual number, but we're just using large high school, so I could say less than 10% of students at a large high school. And then the large counts condition. Since we are assuming the null hypothesis is true unless we can prove otherwise, we're going to use 0.25 for our large counts condition. So when I check n times p naught, the p-value from the null hypothesis, I'm going to take my sample of 200 and multiply by 0.25. So 50 is at least 10. I'm going to do the same thing with the complement of the parameter in the null hypothesis. Which is also at least 10. We have met all the conditions for our hypothesis test. We could go ahead and actually run the test. So that's what we need to talk about next, the actual doing stage, the calculations. So for that free thrower problem, excuse me, because the sample proportion was less than 80, there's some evidence against the null hypothesis. There's some evidence in favor of having a population parameter of less than 80%. But we're trying to see if there's convincing evidence. Rather than doing a simulation to see how unlikely this might be, we're going to actually calculate the p-value, the probability that we would get something this low or lower if he actually is an 80% shooter. So we need to talk about what our mean and standard deviation are for this distribution. So for now, we're going to assume that the null is true because we don't have evidence otherwise yet. Consider the sample proportion p hat of made free throws in a random sample of size 50. We're talking now the sampling distribution of all p hats. So this would be like that one day forever ago where we came up to the board and a bunch of you put p hat values on the board. So we'd get all these p hat values if you just repeated this process. And what would eventually happen, it would look approximately normally distributed. The center we said is whatever the population p was, and then we had a formula for the standard deviation. So that's what we're referencing here. So the mean of the sampling distribution of sample proportions, what am I doing? Sorry. The mean of the sampling distribution of sample proportions is p, which for now, again, we're going to assume is 80%. So it should be centered at 80%. The formula for the standard deviation is the square root of p times 1 minus p over n. So for this problem, again, we are assuming p is 0.8, 1 minus p is 0.2. This was going to be used with a sample of size 50. So I'm seeing the typical distance, our p-hat values are going to deviate from 80%, if we repeat many, many, many times, is about 0.0566. So if I had access to the book and the scanner and everything, I would have scanned in this image. So instead I just tried to draw it. So we can see again, normally distributed, we see the center value at 0.8. I already went ahead and drew in multiple standard deviations, but this is saying 0.0566. So I went ahead and just added and subtracted them a bunch of times. I should use a smaller font size. However, we are interested in the likelihood of the p-hat value that we found. The p-hat value from the sample would be around right here because we got a p-hat value from his sample of 50. It was about 64%. So what we're looking at then, how unlikely is it that he gets something this low or possibly even lower than that, provided that the center actually is at 80%. That's what we're finding when we talk about a p-value. So again, it's normally distributed because of one of the conditions that we checked. I think that's the one I was using. That condition is the large counts condition. So remember, large counts gets you normality when we're talking about proportion. So because the large counts condition is met, the sampling distribution of p-hat will be approximately normal. We just looked at that. to assess how far the statistic is from the null parameter, where you need to standardize this. So I need to turn that into a z-score. So remember, z-scores are always the actual value minus the mean. So the actual value in this case is that sample proportion. The mean we said was, I'm going to come back up here. We said here our mean was going to be 0.8. Remember, this is when we assume that this is true. So I'm just going to go ahead and put P naught, because our mean is going to be whatever we're assuming to be true in the null hypothesis. And then we're going to divide by our standard deviation formula we used earlier. So I'm just going to go ahead and put in the formula. We are putting in the P naught value times 1 minus the P naught value over whatever sample size we're working with. Sorry. So for this problem, sample proportion was 0.64. We're assuming it's 80% until proven otherwise, and we just found 0.0566 for the standard deviation of the sampling distribution of sample proportions. When I put that in my calculator, I get negative 2.83, which we should have expected a negative. When I kind of sketched that in, it was to the left of the mean, so the z-score will be negative, and it is slightly more, not slightly, almost 3 standard deviations away. So that's what that z-score is showing. We just found what's called the standardized test statistic. So standardized meaning it was turned into a z-score. It's measuring how far this sample statistic is from what's assumed to be true in the null hypothesis. How far a sample statistic is from what we expect if the null hypothesis were true in standard deviation units. So our formula is always the statistic, which is your sample number that you get, p hat, minus the parameter. This is what we assume to be true in the null. And it's divided by the standard deviation, sometimes referred to as the standard error of the statistic. I'm pretty sure the AP formula sheet writes out standard error of the statistic. Real quick side note, I hear my children running upstairs above me. If you heard those thudding sounds, and also if I just suddenly turn off the video, it's probably because they came in to interrupt. So hopefully it doesn't happen. So the sample proportion of p hat of made free throws we now know is 2.83 standard deviations below or less than the null value of 0.80. So if I'm trying to find the p-value, I'm trying to find the probability of this. You could use that table, or we could use our calculator. We already know it's normal, so I'm just going to use normal CDF. We are going below this z-score value, so I'm just going to put negative big ol' number. Here comes my son. My apologies. Hey, buddy, what's up?
I'll play with my mom for get here.
No, I don't think you need to play in here. Why don't you play in that room right there? Go build him a house or something.
No, I want to play no sleeping.
Well, build him a house to knock down. He's really strong.
No, he will. Hey, Mom.
What, Ben?
I gotta get Clifford and play around my room. I bet him in my tower to knock down. He gotta play. Break.
That sounds good, buddy. Don't break him. Sorry, I screwed up at first. Since I've standardized it, I need to use my standard normal values, not the actual values for the sample distribution of sample means.